Log on, tune in, find out. Another good idea from Cambridge.
While you're doing that, I'll introduce you. Okay, so our next speaker is Angela Dean from The Ohio State University. She's going to talk today on non-collapsing space-filling designs for bounded regions. Angela.
Okay, thank you, Derek. So this is joint work with Tom Santner and our joint ex-PhD student, Danel Dragulic, and Tom has volunteered to answer the questions. Okay, so first of all, I'm going to talk about some motivation, what made us start looking at this problem, and then I'll talk about the issues later on. Okay, so this is a real experiment that Tom was involved in with some researchers at Cornell University, and it was to do with modeling compressive strains in the bone as a function of the humeral implant position in an elbow prosthesis. Okay, so there's the prosthesis, and here it is inserted into the elbow. So Hayek here was a student who was modeling this, and he used 4 variables to specify the implant position. And for this talk, it doesn't matter exactly what these variables are, except to note that if you're going to put an implant into an elbow, you're not going to put it in backwards so that the arm bends a different way. You hope that the arm is going to bend pretty much the same way as a real arm. And so there are some restrictions on the possible values of these x's. And so we're working in a constrained region. And you can see that x1 and x4 here, that will give us our normal square that people have been talking about earlier today. But here in the middle, that region is actually a diamond. So we have a 4-dimensional region where 2 of the variables are constrained in a diamond-shaped space. The second example, which turned up almost the same year, almost the same month, came from mechanical engineering. A PhD student from mechanical engineering came over to talk to us, and what he was trying to do was investigate relationship between cracks and delamination. This is a machine tool coating we're talking about. Here's the steel, and here are layers on top of the steel to make the tool last longer. And so he wanted to look at cracks are a problem. There's a vertical cracks. Delamination is where this surface peels off the tool as a function of the number of coats and the thickness. So here we have an example where there's a number of different coatings on here, and the coatings are of 2 different types. This is titanium, and I think it was titanium nitride. That's the hard layer. That's the one that's going to make the tool wear a long time. And it doesn't bond very well to the steel. So there's a layer of titanium in here which makes it bond better. So these layers come in pairs. And so he wanted to design over a region where you might have 2 layers, or 4 layers, or 6 layers, or 8 layers. Each layer had a minimum thickness, otherwise the manufacturer can't manufacture it. And the total thickness of the whole layer was also constrained between 2 values, and that was a requirement from the manufacturer that he was working with. Now, to make things easier for today, I'm just going to look at the 2-dimensional space, but the ideas that we talk about in 2 dimensions will also carry over to the higher dimensions. So the 2-dimensional space looks like this. The bottom corner is because the layers have to be of a certain thickness, and then no, let me go back. The corners cut off here are to do with these 2 constraints here, and then the fact it doesn't quite go to the axis is to do with the thickness has to be constrained below. Okay, so that's the shape of the region that we're working in for this second example. Okay, so in each of the examples, a design was required at which to run the computer code that implemented the mathematical model that lay behind this. And many people before me have talked about the fact that if you want to fit a flexible Gaussian stochastic process model, we want the design to be as space-filling as possible within the input region. So first of all, well, what do we mean by space filling? And several speakers this morning talked about different criteria for space filling. For this talk, I'm going to talk about a combination of maxi-min distance and average reciprocal distance. But in terms of the algorithm that I'm going to talk about, if you don't like that particular criterion, you just lift that out of the algorithm and plug in your own criterion. Okay, so maxi-min, as probably you all know, we take the distance between two design points, we find the smallest distance, and then we find the design in a certain class that maximizes the smallest distance between the design points. And you can define distance any way you want. Here, if that z were a 2, that would just be Euclidean distance. Average reciprocal distance, here we have the reciprocal distance. Now I'm defining this average reciprocal distance over a set of dimensions. So various different speakers have talked about projecting down into smaller dimensions. And so if we're thinking about a screening setting where possibly a few variables will be important, we want the design to be space-filling in those lower dimensions. And so you can pick a set of dimensions that you're interested in, and then you can define this average reciprocal distance over that set of dimensions. So if we go back to the formula here, what we're looking at is, here's the reciprocal distance between two design points projected into a certain subspace of dimension little j. Now this is normalized because distances in one dimension are not the same as distances in two dimensions and so on. So we normalize that distance, we add over all the design points in that subspace, we add up over all possible subspaces of dimension j, and then we add up over all of the dimensions of interest, and then take the average, and that's the average reciprocal distance. So there's maxi-min. We could have done that with maxi-min as well, but for this talk I've just got maxi-min defined in the d-dimensional space. It's been pointed out before that as you add design points, you don't want to recompute everything, so with the average reciprocal distance, as you add points, you can update the distance formula. Okay, so how do we combine these two distances? We just did it this way. We took all the designs in the class and rank ordered in terms of minimum interpoint distance, and did the same thing in terms of average reciprocal distance, and then just took a linear combination of those ranks. Now that might not be the best way to do this, but again, it doesn't affect the actual algorithm. You can take that out and plug in your own version of how to rank order designs. Okay, so the reason that you might be screening, I've heard several speakers talk about the fact they may have thousands of inputs. I think Grant Ryman earlier today talked about, was it thousands of inputs, but only a few may be important, and I think Bertrand and Hugo both were talking about screening as well. So you may have engineering design inputs, that's the actual design of the prosthesis or the machine tool. Inputs representing how the device is going to be used in practice. With the elbow, is the person going to be drinking cups of coffee or playing tennis? And then other inputs associated with the actual mathematical model that's being underlying the computer code. We don't expect them all to have a major impact of the response, and so as was talked about a few minutes ago, replication is unnecessary. And so if we're screening, we don't want the design to be replicated in lower dimensions. So not only do we want the design to be space-filling, we also don't want to have replication when projected onto subsets of factors. We're going to call those designs non-collapsing. Okay, this is a similar picture to the one I think both Bertrand and Brad, I think, put up. Okay, so here's an example of a collapsing design. Supposing you've got two variables, x1 and x2, and x2 actually doesn't affect the response. If you use that kind of design, you've got the same response twice at each value of x1, and so you've lost half the information. So you want to design staggered, and we've heard many people talk about Latin hypercube designs over the course of the day, and those are examples of non-collapsing designs over a hypercube. But we don't have a hypercube, so we can't use a Latin hypercube design. So we want a design that's space-filling and non-collapsing over whatever the shape of the space is. Oh, well, I'm sorry, I forgot to do that one first. So there's a three-dimensional Latin hypercube design from Alex Forrester's book, and just showing it's non-collapsing in 2 dimensions and non-collapsing in 1 dimension as well. Okay, so our examples, we can't use this Latin hypercube design because we have a bounded region, and I'm talking as though our regions are bounded by planes, hyperplanes. But if I've got time right at the end, I'll show an example of where we have a ball-shaped region. Okay, so this is kind of difficult because you can't get your design matrix the way you would do with a Latin hypercube design, because you can't choose the variable levels independently. And if you've got a very large problem, you can't do a complete search over a grid just because of time problems. So what we tried to do was to do a sequential approach to this problem. And we looked around the literature to see what was out there, and we couldn't find very much, although I suspect I may have missed something. There's a paper of Trossit's in 1999 formulated as a nonlinear programming problem, but those designs don't need to be non-collapsing. There's another paper of 2003 which is also formulated as a nonlinear programming problem. Again, the designs don't need to be non-collapsing. And our problem with comparing with this paper is that they use a particular nonlinear programming solver, which, if you're in academia with all the budget cutbacks, you can't actually afford to buy. So if anybody knows of nonlinear programming, a nonlinear program software that we could use at very small cost, like 0, please would you let us know. Okay, there's another paper that came out after we wrote our paper, so we haven't compared with that one yet. And I want to talk to Jack because we may have missed something. Okay, so let me tell you a little bit about our proposed algorithm. We're calling it CONCAD, Constrained Non-Collapsing Design. It builds a design matrix column-wise, so that's like going from dimension to dimension to dimension, or variable by variable by variable. And so we start off with the first variable and we choose a good design for that variable, and then given those values and the constraints, we then move into the next dimension and so on. And I'm going to show you a picture. In picture form, it's much easier to understand. So the algorithm builds designs from a grid which adapts dynamically to enforce non-collapsing, and by using the criterion of choice, you can also enforce the space filling. Okay, so I'm going to use this mechanical engineering example in 2 dimensions just to give you an example of how this algorithm works. So we start off in the x1 dimension and we build a grid, and of course that's one thing we have to choose, is what the grid size is. And to get this algorithm going, we're just going to start by picking a point at random. Now you may wonder what this grid is doing out here, because that's not in the region, but we haven't finished. Eventually what we're going to do is grow the grid up into dimension 2, and so this point here is valid because it's going to grow up into the region. Okay, so pick a point at random. I don't know how well you can see that, but there's a number 1, red number 1 sitting on there. Okay, now I don't want any other points. I don't want any other points up here because I don't want it to be collapsing back down into dimension 1. That means that I would lose all of this grid point up here, this grid line up here. And what's going to happen is if I keep losing grid lines, I'm going to actually run out of room before I can build my entire design. So I don't want to lose grid lines. What I'm going to do instead is take the grid line that's underneath here and move it either to the right or to the left. Just flip a coin, and there it is, moved to the right. Okay, so I got the same, here's my point number 1, I've got the same number of grid points along here that I started with. Now I'm going to pick the second point, and if I use my space filling criterion, it would presumably come out down in this corner. I'm not going to put it right down there because I want you to be able to see what's happening in the second dimension. So I've moved it in a little bit. There's the second point, and that grid point, notice, has moved over there to the left. Now we're going to take the third point. And again, we would normally use our criteria, and the criterion probably would pick this point over there, and again, I'm not going to go that far into the corner. Instead, I'm going here, and that grid point moved over. So I'll just do 3 so that you can see what's happening. So in dimension 1, we've picked all the points that we need to pick. Now I want to move into dimension 2. So I'm going to take these 3 points, and I'm going to grow the grid up into the region in those 3 points. And there's the new grid, and now I'm going to start again. So now I'm going to pick a point at random, somewhere in that space. Okay, there it is. Now I'm going to use the criterion to pick the next point, which would probably put it down here, I would think. But again, I'm not going to go down there. Where did I go? Whoops. Can you see where it went? Oh, I know, I forgot to move the grid. That's the problem. All right, so let's go back. So here's my, here's the point I chose. Now I've got to move the grid it's sitting on in this dimension and this dimension, move it both places. Okay, so let's take the vertical line here. There's not much space over to the left, so I'll move it over to the right halfway. So there it is moved, and now, and now I've got to take the horizontal grid line and move that either up or down, and that's the same space, up or down, so I flip a coin, and there it is, moved downwards. Okay, now I'm going to pick the second point using my criterion, which would probably put it over there. I'm not going to go that far. Here it is. I've picked a point down here. Here's the grid moved over, and the horizontal grid line moved up. Now I'm going to go for the third point using my criterion. Here it is over there, and the grid it was on has moved over there to the right, and the other one has moved down. Okay, so now I've finished. If I had a third dimension, I would go from those 3 points, and I would grow the grid into the third dimension. So you see that we're not adding complexity as we go along. We've got the same number of points always as we go along. Okay, so we have 2 things that we have to decide. One is grid density, so how many grid points do you want in each direction? And the second thing is that it's a good idea to carry more points than you want to end up with, just because we're doing this sequentially, which is not the best thing to do if you want an optimal design. So it gives you more flexibility if you're carrying more points than you need, and then right at the end you'll pick your best endpoints. So at the moment we're recommending grid of a size 100 and carry 3 times as many points as you want to end up with. We may change this one and make the grid size related to the number of points as well, but we haven't looked at that yet. Okay, also, which is not really a tuning parameter, but remember the start is a random selection, so every time you run this you will end up with a different design. So it runs fairly quickly, at least in the smaller problems that I've looked at so far, And so it's a good idea to run the algorithm several times and then you pick the best design out of the ones that you've generated. Okay, so let's see what it gives us for this mechanical engineering problem. Remember that was the design space. All right, let's look back at our criterion. Remember we were going to rank order the designs according to the maxi-min criterion, rank order the designs with respect to average reciprocal distance and take some linear combination of those ranks. If you set alpha equal to 1, you get the maxi-min design and it looks like this. If you set, this is just with 10 points by the way, if you set alpha equal to 0, you get the average reciprocal distance design, which looks like that. And if you set the alpha equal to half, you get a sort of combination, which looks like that, which we thought looked better. But again, we've only got 10 points here, so it looks as though it's got lots of holes in it, and that's because there aren't many points. So what did we get for this design? This was a 4-dimensional design with constraints on the x2 and x3. If you set the alpha equal to 1, you get the maxi-min design, which looks like this. Now they only wanted 10 points for this design. Now you can't see the diamond shape too well, but the reason that there's no points there in the corner is there's the diamond's constraint right there. If you set alpha equal to half, you get that design. You can really see that diamond coming out there now. And again, it would be up to the user which kind of criterion you picked, or you could replace those criteria with something else. So the highlights, we have space filling at the moment. What I've demonstrated is in the sense of maxi-min and average reciprocal distance, but you can replace that with your own criterion. The designs are non-collapsing. This scales up well in the number of dimensions because we're not adding complexity as we go from dimension to dimension. I mentioned this before. We recommend at the moment 100 grid points. Every time you grow a grid, any grid line has 100 points on it, and carry 3 times as many observations as you want, and run the algorithm multiple times. Okay, something that was talked about yesterday, both Dave Higdon and I think it was Peter Challoner talked about extending designs. So you have a given design and you want to augment by picking extra design points. I'll show you an example of that in a second. And we can also extend this to non-polygonal regions. Okay, so here's a very hypothetical example. Supposing that you started off with a Latin hypercube design in the 2-dimensional space, and you fitted a model and you found out that actually the region of interest, or you changed your mind later, that the region of interest was this one here. Now unfortunately we've only got 4 points in that space, so what we'd like to do is add say 5 more points to fill up the space. I don't want to start again. I've already got 4 very good points and it's expensive to run the computer code. So let's use that algorithm. Instead of taking a random start, we've got 4 points already. We can now build on those using the algorithm and fill up the space. And this was a maxi-min criterion. So those blue points are the ones that get added, and then that's the resulting design in the space given those 4 original ones. This is an extension to a 2-dimensional ball or a 10-dimensional ball, and this is the 2 algorithms from the Stinstra paper, and I won't look at Trosset because that gets beaten by Stinstra's algorithm. The more sophisticated algorithm can't handle the larger number of points, so let's just concentrate on this column and our column here. Okay, so this is maxi-min, so large numbers are good. 2 dimensions, that's a circle, 10 points. Stinstra's maxi-min design has a minimum distance of 0.3522. Ours is not quite as good, but then our designs are non-collapsing and his aren't. So that constrains us. We wouldn't expect to be as good because we don't have as much flexibility in the space, but we're nearly as good. And the same thing for higher dimensions here. We're a little bit worse than his, but not, in my opinion, not considerably. And then in 10 dimensions, oh no, let me go back a minute. We're better here, 100 points, yeah, we're better. I'm selling us short. And we're better here. It's in 10 dimensions we don't do quite as well. However, again, we have non-collapsing designs and the Stinstra one doesn't. So, thank you.
Questions? Right. Oh, go for it.
Could you go back to the figure? Yes, this one. What would be wrong with the simple approach where you would generate a standard, whatever, Latin hypercube sample, and then you look at the picture and you realize that the points in the upper right corner and the lower left corner are not acceptable, and you just execute the remaining runs, the remaining points. They are non-collapsible, they are space filling.
Yeah.
Maybe your complaint will be it's not enough points, so what you do is you start with a bigger Latin hypercube sample so that you are finishing with enough points.
Okay, so the question is how space filling are they?
Any Latin hypercube sample is space filling, right? So
Well,
if I start,
over the whole region it is. I don't know about a sub-region.
is that so?
Well, I mean,
You get a design
you
point down
know,
diagonal,
we've
right?
got a big
what I meant.
hole.
It's
here.
non-collapsing, that's for
It's
sure,
non-collapsing.
but it might not be space filling.
It might not be space filling under a particular criterion that
Yeah.
you pick. It might be, but it might not
Yeah,
be.
yeah.
Yeah.
Because I found in a simple situation, that's
Yeah.
the naive approach I found.
Yeah. Yes. Yes. Yes, it is. But what we found was it may not be
Space filling.
space filling.
It's non-collapsing.
yeah. Yeah.
So let me just ask you, by the very nature of having constraints, doesn't it mean that all variables are important in some sense? I mean, you're not going to really
No.
collapse X2 because you need,
Um,
it's part of the constraint, right?
let me go to the second one here. Whoops, where's it gone? That one. Well, it's only two-dimensional, doesn't it? Okay, so the question is, by the very nature of having constraints, doesn't it mean that all variables are important?
They're part of the model from that point on.
That's a good question. I need to let me ponder that one before I.
It can be
give it
constant
a-
across the spin.
Yeah, I mean,
area
you can
of
have something that's
interest.
very flat in one direction, and hence it's
Well, it's not zero, right? But still, you can't abandon X2 because if you said, if somebody comes along and types X2 is equal to 47 and the constraint is that X1 plus X2 is equal to 10 or less than 10, it's still always part of the model.
But it doesn't mean it's an important variable in
I mean,
terms
the-
of the response.
If the y doesn't vary, I mean, if it's flat when I track along any x1, then it's not important.
Well, it has to be zero, right? Unless you've actually, in a computer model, it's got to be zero to be negligible.
Why 0?
Well, then you get.
Why couldn't it be 10 all the way across? It can be 10,
Yeah,
10.
Oh, sorry, the change has got to be zero.
Yeah, the change is going to be 10.
Correct.
Yeah, I'm not sure it's ever happened, but.
So in this region here, all of these, all the way up this line here,
Oh,
we could get the same response.
Yeah, so I guess all my point was is that
Yeah.
if you're going to use an emulator,
Yeah.
X2 always still has to be part of it because you have to be able to reject places where you're not it does not fulfill the constraint. That's all my point was.
But it doesn't
Oh,
necessarily, it doesn't interfere with estimating the parameters for the others because it doesn't have any effect, or potentially could have no
Absolutely.
effect across
That's-
I mean, if I was going to compute any kind of main effect sensitivity index, I want it to be 0 for such a variable and, something else for the other variable.
That's right.
Yeah.
But X2 is still part of it because you got to make sure it's part of the integration region.
Yeah.
This is a related question. And the question is what are the variables here? And it relates to the non-collapsibility. If you look at the diagonal, if I understood it right, the diagonal is the total thickness.
The diagonal was the total.
That's the total thickness from the
Yeah.
two layers together.
Maximum.
Oh, that one's the maximum.
That's the
but
maximum
The
total
diagonals
thickness.
across here
Maximum
are the
total
thickness.
Maximum total thickness, right?
Right.
But if you thought about the total, well, but I mean, if you look at any diagonal, it's the total thickness.
Yeah.
That's one total
Yeah,
thickness.
a
And if you go down
line, any
diagonals.
line.
So
through
for
there
example,
would
if you thought the total thickness of the tool was the more relevant variable,
be- Right.
you've got, and one of the things that comes out, and if you look at your designs, they do put quite a few points right on the constraint. So if you would, for example, if you were to think that that might be the more fundamental variable, then the design actually has a lot of collapsibility in it. I just wonder if that's something that you've thought about.
I don't think I understand
you
you.
rotate
So,
That's right. I mean, if you looked at the variables
Yes.
not as being x1 and x2, the
Yeah, I
two
know,
layer
but they've still got to
thicknesses, let's say
manufacture.
the total thickness and the ratio of the two thicknesses.
Yes, okay.
In
And
terms
then,
of the total thickness, you're getting a design that actually repeats quite a few values for
oh, I
total
see.
thickness.
Oops. On here, like
Yeah.
down here, all the way
Yeah.
down
Right.
here.
Right.
Yes, so we've got 3 on the same total thickness, that's correct. Yes. Yes.
Presumably, this would require some understanding of the
Yeah,
engineering
something-
and how this thing is functioning, and why one particular
However,
formulation would be more fundamental to the engineering of the problem.
yeah, yes, but the, let's see. So we got x1 and x2, but it's the same total thickness, but x1 is the thickness of the titanium nitride, and the other one is the thickness of the titanium. So those points are not. I mean, they're going to have quite different y values, right? So that, I mean, I understand what you were getting at, but
Okay.
I
So
don't
in this
think
particular
that's-
example, that wouldn't look like it would be the.
But maybe not, if it didn't matter what type of material it was, and if the lights really only depend on total thickness,
Mhm.
we'd be
Then
in
it would
trouble
be-
with that design.
Yeah. Yes. So that would be a different kind of point. Whereas here, they actually were interested in the thickness of the different layers, and even if you looked at the layer closest to the steel, if you had the same material, the same thickness further up, you know, if you just swapped 2 like that, you'd still get a different Y. So it's not interchangeable.
We have cases where we know whether any individual point is inside the allowed region or not, but we can't actually draw it for you because we just have a criterion.
Yeah.
Would this work in that instance?
Yes, I think so. As long as you could tell me what the candidate set was, you know, if I could ask you, is this point in your set or not, then yes, it would
Any
work.
point you can say whether it's in the set or not, but you can't actually draw the boundary.
Yes, as long as you can tell me whether, if I give you a grid, if you can tell me which ones are in the set and which ones aren't, then this will work, yes.
As long as the set's convex.
Yeah, sure.
So, before we thank Angela and the other speakers one more time, there's a poster session that started 2 minutes ago, but everybody else is still here, so that's good. So please make sure you attend the poster session. Tomorrow we start at
9:30.
9:30. And any other announcements? Brad's buying beer. All right, well, let's thank the speakers and Angela.